In this video, we are going to expand our knowledge of vectors into 3-space. Now that we know what 3-space looks like, we could start talking about what a vector should look like. So to add a third component to a vector, remember before in 2-space, we had something like this, right? That was my 2-space, x and y. So now we just add our z component. The vector still explains the same thing. It's a direction and it's a magnitude. That's it. It doesn't live anywhere in space. It just describes a direction and how long. The zero vector is still 0, 0, 0. We have new unit vectors. We have an I and a j, except for now we have to add that z component. So they're not just 1, 0, and 0, 1, but they're going to be 1, 0, 0, 0, 1, 0. And then we get this new k component. That's our j. So k will be 0, 0, 1, meaning my new vectors in 3-space will look like that, or component form like that. How you draw these, I wanted to show these pictures here to help you sketch if you need to. Use that XY plane, like a shaded area like that, and you just draw it and maybe shade it in or just however you want to do it. But notice these like red X lines are how they show their space in 2-space. And it really does accomplish the 3-space thing, because without those red marks, imagine what that vector could look like. It's kind of hard to describe where it's at. So if you are sketching and you need to draw them, that's how we do that. Now, the only thing we haven't talked about so far with a vector in 3-space is how do we come up with vectors if they give me a point, a starting point, initial point, and a terminal point Q. It's the exact same thing. I just subtract each component. But now I have a z component, so I just subtract my z's. All right, so those are vectors in 3-space, 3 components, I, j, and k. K is still an unit vector. You can see it over here. It's just in the z direction. All right, here are some properties. I'm just going to talk through them pretty quick because they extend from 2-space. Equality of vectors. If u and v are equal, then each component have to be equal. So the x component, y component, z have to be the same thing if they're equal. Component form is written like that. If I want to find, here's an important one, the magnitude. Notice it's just an extension. It's kind of nice. I just take my third component, square it, and add it in. Unit vector is done the same way in 3-space. So you just find the magnitude and divide it. Vector addition and scalar multiplication are exactly the same. Add your x's, add your y's, add your z's. If you're multiplying by a scalar, distribute to all 3 parts. All right, let's get an example. Find the component form and the magnitude of vector v having the initial point. I'm going to call these things, I just prefer it, p and q. Then find the unit vector in direction of v. Okay, so v, or in this case, I'm going to go ahead and do this p, q. I take q, and I do 0 minus -2. Be careful with that. And then -4 minus 4. That's not 0. Be careful with that one. And then 4 minus 3, giving me all 3 here. So this vector is 2, -8, 1. They want us to find a unit vector in that same direction. So I'm going to find its magnitude, because if it is a unit vector, I'm done. If not, I got to use this to create a unit vector. So I square 2, I square -8, and I square 1. So I get the square root of 4 plus 64 plus 1, which is the square root of 69. All right, to find my unit vector v, put a hat on it now, I do 1 over the square root of 69 times 2, -8, 1, and we just distribute. And you don't have to rationalize. There is my unit vector. So it's the same idea, same process as 2-space, except for we add a z. Just add the third component. There's a very ugly v here. Sorry for my second grade handwriting. I know it's not the best, but I think it's legible. So hopefully it is. Okay, so we have to move to a new definition, a parallel, given vectors. Now, for 2 vectors to be parallel, they have to have the same direction. They just have to move in the same direction, right? Length doesn't really matter. All they have to do is run exactly in the same direction. The whole doesn't touch thing doesn't work here. I want you to imagine take a highway and a bridge that passes over the highway. Those two, the bridge and the highway underneath, never touch each other, right? One's a little higher than the other. They never run into each other, but the highway and the bridge that cross, it doesn't even matter about the angle of the bridge. They are not parallel. They never touch each other, but they're not parallel. Three space adds this whole new dynamic of that the lines can be on top of each other, but like in planes that are parallel, like a whole sheet of paper, infinite sheet of paper. One plane lives on one piece of paper, and then another piece of paper underneath it. That their line lives on that one, and they never touch each other, but they don't run in the same direction. So it's very different than the definition that we've kind of grew up knowing, that they never touch. That's typically my student definition. The actual definition is they run in the same direction. So what that means is two vectors are parallel when there's some scalar c such that we have this. Now, I don't know if you remember I think it's in the first or second video, one of those early videos where we had like this like list of, we had these lines and we had these vectors that were spitting out, and we were like talking about like the form here that if I multiply by a vector or a number c, that those always point in the same direction. The only thing that changes is the length when I multiply by a number. So that's why we have this definition, because if I just multiply by a number, it changes the length of my vector, but it doesn't change the direction it runs in. So we have to be able to find something that multiplies to get to the other. Now, there's going to be a later definition here in a few sections that is a little more, I don't like these methods that are like, if you can find this, then it is this. If you can't find, then it's not. Because I could look for hours and not find anything, but that doesn't mean it's not there. So we will have a new formula for this coming up in a couple sections to determine if they are parallel. But as of right now, what we're looking for is to respect this relationship. So let's look at our example. It's a little easier getting some under our feet. So vector W has initial point. I like just to name these. It's just habit of mine, P and Q. Which of the following is vectors is parallel to W? So I'd like to find W first. So W is equal to, okay, I subtract all my points. I got -4 minus 2, 7 minus -1, and 5 minus 3. So that tells me that W is equal to -6, 8, and 2. All right, so that's W. And we're asking ourselves now, is there a C that I can multiply by U and get W? So I'm going to write that in. C times 3, -4, -1 equals -6, 8, and 2. I'm going to move this because I need the room. Cool. All right, so there's W, and I'm just looking for a C now. So this gives me 3C, -4C, -1C equals -6, 8, 2. So I just look at this. I take this first one. Let me draw arrows here. I take these two, and I get 3C equals -6, right? Because those have to be equal. That tells me C must be -2. And now I have to check, does this work with the other ones? So the other ones were -4C equals 8 and -1C equals 2. So the question is, does it apply here? Well, if I plug in C, I get -2, I get 8, and I plug in -2 for the C on the bottom, it works. So U is parallel with W. There's my symbol for parallel, 2 straight bars. You can use that. Okay, so let me rewrite that because it looks like I wrote it with my toes. There we go. Not much better. Okay, so what you do is you set it up. We know the definition that they're parallel if there's some multiple, because a multiple changes the length but doesn't change the direction. So we set that up here. Then we answered it for one of them, which got me here. All right, we used that to get down there. And then we went that way and checked it for the other two. If the other two work, then that leads there. All right, so we set it up, checked one, found the answer, tried it on the other two. If it works, they're parallel. If that doesn't work, they're not parallel. All right, so let's do V. So we do C times V equals W. So C times, okay, V is 12, negative 16, 4, times negative 6, 8, 2. Now, this definition can change, and I see that I have big numbers going to small numbers, so what I'm going to do is I'm going to put that C over here. It can be on either one, right? It doesn't matter, because now I'm just asking, is the other one parallel? It's the same question. So I'm going to put that there. So I get 12 equals negative 6C. I also get negative 16 equals 8C, and I get 4 equals 2C. Okay, this spits C equals negative 2. This spits out C equals negative 2, but this one spits out C equals 2. So V, I do my parallel symbol and I put a slash through it to say not, is not parallel to W. I put a U and a V here, and it should have been a U and a W. Forgive me. All right, so the first one is parallel because I was able to find a C. The second one was not parallel because I found my C's and they're not all the same. You could do it that way as well. Find one C, check to see if the other ones are true, or find all C, and if they're not all equal, then they're not parallel. There is another way to do this we will learn in a few sections. All right, we're going to keep going. There's quite a bit of examples for this one. We're going to determine whether points are collinear. Collinear means they all live on the same line. So let's draw a line, and we're going to put P, Q, and R to think about it. P, Q, and R. Okay, so if I do this, if PQ runs in the same direction, I chose the same color, as PR, then Q would need to be on PR if they run in the same direction. So what I'm going to do is find a PQ and a PR and see if they're parallel. All right, so let's just do PR first. The vector PR, so that's here and here. I got 4 minus 1, 7 minus negative 2, and negative 6 minus 3, which gets me 3, 9, negative 9. I also need PQ. PQ would be these two. So 2 minus 1, 1 minus negative 2, and 0 minus 3. All right, that gets me 1, 3, negative 3. All right, so I'm going to do C times PQ equals PR and check to see if that equality holds. So I got C times PQ, which is 1, 3, negative 3. The reason I picked C to go with PQ is it's smaller. 3, 9, negative 9. So this gets me 3 values. I got C times 1 equals 3. I got C times 3 equals 9. And I got C times negative 3 equals negative 9. All of these give me C equals 3. So they are collinear. Since they are parallel, the two vectors PQ and PR are parallel, these two here, that means they lie on the same line. So we're going to say points are collinear. Cool. All right. Makes sense. If they are parallel, then they are collinear. So I guess we should have wrote that too. PQ. Let's make sure logically we're on the right path. I'm going to write this here. Sorry for squeezing this in. PQ is parallel to PR, which implies, double arrow, implies points are collinear. There we go. Okay, we have, I think, one more problem here for this video. Yep, for this video. I'm just going to run through a few more ideas of vectors. Okay, so there is how to tell if 3 points are collinear using vectors. We could have also created lines and checked slopes. We have done these problems. I think you've done those problems in probably a pre-calc 1 class or high school algebra class. Okay, so this next example, write the vector in component form. I want you to notice something. You don't need to write this, but I want to point it out. I got 4I plus 0j minus 5k. I don't know if you noticed that it's not a two-dimensional vector. It's a three-dimensional, but it's missing the j. So if I wrote it in component form, then component form is 4, 0, negative 5. Be very careful of this. I find myself making this mistake a lot, just thinking fast, doing like, oh, okay, two-dimensional vector, 4, negative 5. No, it's a three-dimensional because they gave a k. That's the indicator. Okay, they want us to find the terminal point if they give me a vector and give me an initial point. Okay, so remember a vector, I'm going to write it in component form, are just directions to get to the next point. So if I say the initial point is negative 2, 3, 5, to get to Q, or my terminal point, I'm going to use the vector as my directions because that's what it explains. So if I start at negative 2, the vector says to move 7 in the x direction. So this Q is a 5 in the x. I started at 3 and it says to move down 1. So this is a 2. And then I started at 5 and the vector says to move 3 in the z direction. So that is an 8. So there's Q. I like these problems because it really does show me if you understand what a vector is and how it works. All right, find the magnitude of this vector, then find a unit vector in the direction of v. Okay, so I have v. I'm going to find its magnitude first because if it is a unit vector, I'm done. Okay, so the magnitude is going to be negative 6 squared plus 2 squared plus negative 3 squared. And that's the square root of 36 plus 4 plus 9. What is that? That is 49. Square root of 49, that's nice and pretty. We have the magnitude as 7. Then they said find a unit vector. So I'm going to say v, and I'm going to put a hat on it to show that it is a unit vector. It's going to be 1/7 times the vector itself. I'm going to write it in component form because that's what I prefer. Doesn't matter though. I got negative 6/7, 2/7, and negative 3/7. So there is a vector in 3 space that is a unit vector pointing in the direction of v.